Ernest.
Yeah.
Oscar Wilde, yeah.
You're on.
All right, so everybody, let's get started. So we are very pleased to have Professor Anne-Marie Madigan from University of Colorado Boulder join us, and she's going to talk to us about dynamics and about Oscar Wilde, well, kind of Oscar Wilde, right? This is where it comes from. And before we get started, just a little fun thing. If you've been to Colorado, so it's a beautiful place, lots of hiking, right? And Anne-Marie was testing collisional dynamics in a very personal way. She told me she was biking, right? Yep. Was biking and almost ran into a big dog. But actually, in Colorado, it's not necessarily a big dog. It ended up being a bear. So this is what we call, I guess, dynamics, right? Anyway, with that in mind, please, we'll let you take over. So Anne-Marie is here, so I assume the
bear had a rougher time.
Yeah, the bear had a rougher time.
Okay, thanks so much for having me and for being here today. Yeah, I'm going to be talking about something that's really simple on the face of it, how bodies that move on eccentric orbits interact with one another. And it's going to be important for two systems in particular that I'll talk about. So the first is our solar system, or any planetary system. And the second is stars around supermassive black holes. So let's get started. I'm going to show you a picture of what I think of the inner solar system. Okay, so for some of you this might be too simple a schematic, but we have the sun and we have bodies that are moving on roughly circular coplanar orbits. And all I'm going to be doing in this talk is bumping up the eccentricities of the bodies that are moving around the central object. But you can do this in two different ways. So the first way we can do this is to distribute the orbit randomly about the disk. Okay? And the second way we can do this is pile all of these eccentric orbits now onto one side. So I'm going to show you that one of these systems is extremely stable and can persist for a Hubble time. The other system, just because of its setup, is extremely unstable, and all of the orbits will jump away from each other. So if this was a class, I could clicker question this up, but I'm not going to make you put up your hands or anything like that. I'm just going to tell you that maybe counterintuitively, the one where the orbits are spread out from each other is an extremely unstable system. And I will be applying this to the solar system. The second system I'm going to show you is an extremely stable system. And so this is the outer solar system context that will be showing you that there might be evidence that orbits in the outer solar system have been in this state and have become unstable and jumped away from each other. In the second case, I'm going to be applying this to galactic nuclei, in particular the M31 nucleus, and showing that not only is this system very stable when you have stars moving in this structure around a massive black hole, but it can produce really interesting things like high rates of tidal disruption events. Okay, so before we actually get into just going through those two systems, I have two slides on important dynamics. Okay, because we're just talking about bodies on eccentric orbits gravitationally interacting with each other and changing their overall structure. So this is the typical idea of how bodies interact with each other. It's the classic two-body relaxation that we learn about in Binney and Tremaine. So here we have two bodies, they move past each other, but of course they feel some gravitational acceleration, and highly exaggerated here, they'll change each other's orbits. So this is a diffusive process. It doesn't lead to violent instabilities. It changes the orbits of particles pretty slowly. And this is not what we're interested in here. What happens when we take these two particles and we place them around a massive object, so these could be planets around a star or stars around supermassive black holes, is that they don't just move past each other once, maybe change each other's orbits slightly and never meet again, or if they do, have no memory of what they did before. They're going to be repeating the same orbit again and again around this massive object. And so even if they never physically come right beside each other to have a very strong close encounter, that gravitational force that they exert on each other is going to build up and become very strong. So this is called secular dynamics. The word secular is just coming from a long time scale. Another way of calling this is orbit averaged dynamics. And so we'll do this in this talk. We'll imagine now, not that we have these particles around a more massive object, but that we spread the mass of the particle around its orbit. And we think of the system as being massive elliptical wires that gravitationally pull in each other. There's going to be more mass located at apocenter, because that's where a particle spends most of its time. So they're not smoothly distributed massive wires. They're very kind of top heavy, if top is far away from the massive object. So you're going to see these two equations, so I want to put them up here and explain them properly. The first is obviously the angular momentum per unit mass of one of these orbits. You can calculate that anywhere along the orbit, it's just r cross v. The second is the torque that orbits exert on each other, which is a rate of change of angular momentum. That's just the time derivative, so it's r cross f. So to calculate the torque on one orbit, you should really integrate around the entire orbit, sample all this r and all the forces that are felt at that point in the orbit. But we're not going to do that in a talk. It's boring, and it would just be equations. What we're going to do is just imagine that because most of the mass is located at apocenter, we'll just say, well, what is the force felt at apocenter? And that will give us a rough idea, at least of the direction of the torque. And then how is the angular momentum of the orbit going to change? And that relates to the eccentricity of an orbit. More angular momentum, you're more circular. Less angular momentum, you're more radial.
Excuse me, does it also depend on the eccentricity? I mean, how the mass is distributed, right? Because there's a competition between how much you're elliptical and how much the mass is distributed.
And that's really important. You're totally right. So the more eccentric an orbit is, the more unevenly distributed that mass will be around the orbit. And that's actually really important for the dynamics. Some of the dynamics that I'll show about how the structures actually influence each other through torques shuts off if your eccentricity becomes too low. If you go back to being more circular, none of this works. So yes, it's very important that there's an uneven distribution in mass.
One other question. You talked about black holes before, so general relativity would tend to cause precession and other effects. Any significance to those?
Absolutely, yes. Yeah. This type of orbit average dynamics, for it to be efficient, it relies on the orbit not moving rapidly. Right? If you have two orbits and they don't precess, they don't move, the torque's going to really build up and become very efficient. If you're too far away from a black hole, so there's lots of stars within your orbit, you precess fast. Your orbit opens out fast. And so this becomes not very important again. And as you're saying, if you get too close to the black hole, or you're too eccentric, general relativistic precession will make you precess really quickly too. And so this type of dynamics shuts down. Yeah?
And how small would corrections do to the fact that the planets themselves aren't point particles, but they are either they're oblate and they have these tidal forces that probably depend on their shapes. I can imagine it's a lot smaller than the first order effects on the torque, but do you consider them ever?
No. I think that's a really good point. There's lots of stuff that doesn't go into the simulation, so I think the fact that they're oblate, they're kind of rotating bodies, I think that will be important for some interesting physics that you're trying to explore. When I'm looking at like what's the overall evolution of the structure, I don't think that's going to be the most important thing. There's other stuff I leave out that will be more important that I can get back to. Okay, so that was the whole talk on dynamics. Now we're done. Now you understand everything. So we'll just go through these two setups. So the first is where we're taking something that looks like the inner solar system. Got lots of planets, not that many planets, 8-ish planets on roughly circular, roughly coplanar orbits, and we're bumping up the eccentricities and leaving them kind of randomly distributed, so you have an axisymmetric disk. And I'm going to show you that this is extremely unstable. This is why we called it the inclination instability. The reason we called it inclination instability will become obvious in a moment. Okay, so what I'm going to show you now, in keeping with we're not going to be thinking about point particles and where they are, but think about orbits and how the orbits evolve. What I'm going to show you here is the inner solar system evolution, so we have small eccentricities, not totally zero, because what I'm plotting here are not where the particles are themselves, but one special point on their orbits. So this is their perihelion position, or where their eccentricity vector points to. I think I have a thing here, right? So if we're looking top down onto an orbit, this is keynote, so this isn't actually an ellipse, which always annoys me, but what can we do? This is the point that I'm plotting here in this projection. So I've started everything off on a disk, which is why you see all of these points in a line, kind of like in a mid-plane. I'm going to set this running, and this is results from an n-body simulations where you actually have point particles, but I'm just plotting their perihelion position. And not much happens, or not much surprising happens. You'll see kind of a flow in this direction, and what that is orbits precess. So their pericenters don't always point in the same direction, they move around. And the fact that you see the distribution puffing up a little bit is just well known, two-body interactions. You go from a thin disk to being kind of a puffy torus. So nothing exciting at all. Why would I show you this? It's to show you the difference if we now just bump up the eccentricities in this n-body simulation to a high value. And 0.7 is really what you need. Anything lower than 0.6, you go back to being a normal system we understand very well. Okay, so I'll set this running, and I'll let you see how it's different. Right, weird. Good, good. You have that reaction. Okay, so the first odd thing is that it's like symmetry gets broken. Why are all of the particles all of a sudden moving in one direction?